say it's not. All right, get this video started. So I'll pretty much go through Excel today for the majority of the time. And then at the end, we'll kind of introduce the next topic, which will be related to Learn Smart. You should have gotten done before we started class today. So if you go onto kind of Canvas, our files, in-class data, there's this Indiana weather file. So that's kind of what I'll be working on. So it's got a lot of different worksheets here, but we're going to use that rain worksheet, which we kind of go back to last week. We said it looks like it's pretty normally distributed. Right? Rainfall is pretty normally distributed. So let's say, let me go here. I'm going to zoom in so we can see it a little bit easier. There we go. And I'm just going to get rid of everything up here and everything here and rebuild it for you. Okay. So what was up there was the mean. We can kind of think about, we could find the variance. We could also find the standard deviation. So here I've got kind of annual monthly rainfall. So I could just find the mean by using that average function. Going over here, Control Shift, hit the down arrow, select the entire column of kind of rainfall, right? I could then find the variance. I'm treating this as population data by doing the same thing. So var.p, just select that entire variable. Hit enter. I've got my variance in there. Now, if I want my standard deviation, all that's going to be is the square root of my variance. Right? That's what we've kind of used in the past. So I could set this up pretty easily to do this for kind of overall. Now, if I broke it down by month, one thing that kind of is nice is that, let's say I want to do just June. So look at the average June temperature. So I go over here, select the June variable, Control Shift, Command Shift on a Mac, hit the down arrow. I get the mean June temperature. I can do the same thing, get the variance, go over here, select the variable again. So now I've got the mean and variance for June temperature. I could get the square root, or sorry, I can get the standard deviation by taking the square root of that variance. Well, now if I copy this over, right, instead of column H, I'm going to copy it over one column. It's going to look at column I, which if I look at column I, oh, keep going. Well, that's July. If I do all these months in a row, when I copy these over, it should just be finding kind of the next month's mean, variance, and standard deviation. So I can do it pretty quick. I can get 4 months. If I think about within each month, rainfall is normally distributed, I can start to find the probability of seeing certain amounts of rainfall. So how did we do this? Let's see, I can switch over here real quick. Last class is kind of a reminder. Waiting, there we go. So what I'm going to do is I'm starting out with this rainfall variable. I think in June, the average is like 70.75 or something. I think the standard deviation is 1.52 or 1.53. Oh, this is temperature. I lied to you. This isn't 70.75. This is 4.2. And then I just think about what's the probability that I see 3 inches of rainfall or anything less. Right? So when we did this by hand, we said, well, what we're going to have to do is turn that value of 3 into a z-score, look that up in our table, and the table will tell us the probability I see something below it. And the equation we were using was take the x value you're interested in, subtract the mean, and divide by the standard deviation. So these are the examples that we did by hand. Well, I can do all of this in Excel. Okay? So I can draw this out and have this set up, but I'm going to do it in Excel. So I'm going to do this and leave this up down here in the corner. Okay. Maybe I'll leave it over in this corner. So if I think about June, right, I could basically just use Excel as a calculator. So I could calculate the z-score by taking that cutoff value of 3 inches, subtract the mean June temperature, and then divide by my standard deviation. Okay. Oh, you can't see it. Well, that would help, huh? Hopefully it's only the first time it'll do it. All right, there we go. So I take that cutoff value of 3, I subtract the mean, divide by my standard deviation. Right? That's just my z-score equation. Well, now I know I want the area to the left. So usually I would have to round this to the second decimal. So what, negative 0.78, go to the table, look up negative 0.7, go over to 8, and it tells me the probability. Well, Excel will do that for me. Right? So if I use this norm.s.dist function, so norm.s.dist, I tell it that z value, and then comma, always put a 1. So when I put a 1 here, this always makes it cumulative or returns to me that cumulative density function value for whatever z-score I'm telling this function. And that's what we were doing with the table, right? It was always giving us the area to the left. If you make this a 0, it's not giving you the area to the right. It should return to you. If you put a 0 in here so that it's not cumulative, the probability of any one value should just be 0, right? We should only be able to find, but what this does is it tries to find like a really small interval. For the sake of what we're doing in this class, a 0 here has no use. So we're always going to be using it just like we would the physical table, which is put a 1 here and it always gives me the area to the left. Okay? So I can hit enter there. Now, this was kind of similar to how I did it by hand. In Excel, we often can, what I would refer to as black box things a lot. We can have Excel do a lot of the work behind the scenes for us. So if I use the norm.dist, so norm.s here, right? So before we were using norm.s.dist, which was the standard normal distribution, so using z-scores. If I'm using the original x variable, which was rainfall in June, I just use the norm.dist. It's normally distributed, but its mean is not 0 and its variance is not 1. So now what I can do is tell Excel, okay, take this value of 3. It's coming from a normal distribution, so comma, a normal distribution with this mean, comma, and this standard deviation. And then we'll use comma 1. So what this is going to do, instead of telling it the z-score of what, negative 0.78, and it returns to me this area, I'm telling it, well, look, I want to know the area to the left of this value of 3. So if you tell Excel the mean and the standard deviation, which we did here, it'll take that value of 3, turn it into a z-score behind the scenes, then look that z-score up and give you the area to the left. So it's basically just doing it is calculating the z-score, it's just doing it behind the scenes to where you won't see it, right? So we should get the exact same answer, right? I just kind of skipped this middle step. I mean, I say it skipped it. It didn't show it to you, right? It was doing it behind the scenes. And, then if I wanted to copy this over, now I've got the next 4 months, and I could start to play around with, well, what's the probability of seeing, I don't know, 6 inches or less of rainfall? Or what's the probability in August we get less, 1 inch or less, right? You could play around with these cutoff values because you have them all referenced. Okay? Any questions over any of this? Or let me see this again.
What did you say the norm.dist was used for again, not without the S?
So if we don't have the S there, basically when you're using the norm.s, you already have to have your z-scores, right? Norm.dist is when basically you're just not calculating the z-score, like it's going to do it for you. So you start out with the original variable x, which here was rainfall. Any other questions? See anything in the chat? Okay. So what if instead, let's say I want to find the area to the right, right, or kind of above 3 inches of rainfall. Okay. So what I'm going to do, if I want the area to the right of 3, what's all I have to do here? So if I know the area to the left is 0.21, the area to the right has to be just 1 minus that. Right? And I can do this in steps, or I could put in norm.dist using that cutoff value of 3, comma, select the mean, comma, select the standard deviation, comma 1. So this will give me the area to the left of 3, subtract that from 1, and I should end up with the area to the right of 3. What if, let's use some other data. So I also had the same thing, but for temperatures, right? So I had this by different months, kind of find the probability that to the left of certain values. But what if instead I wanted something like, what's the probability that I'm, I don't know, in between 70 and 72 degrees this June? Right? Well, we're really thinking about there, kind of a couple different ways to think about it. The way I explained it before was you would find the area to the left of 70, find the area to the left of 72, subtract the smaller area from the larger area, and you're left with just what's in between. But why does that work? Well, if we find the probability that, let's say we want x to be between 70 and 72, right? That means every outcome that's less than 70 but above, less than 72 but above 70. So if I just find the probability that x is less than or equal to 72, right, that's every outcome below 72. If I then just subtract the probability that x is, and here not equal to, but just less than 70, what I'm left with is just the values in between 70 and 72. So that's why subtracting the smaller probability from the larger one will just give me with what's in between. Well, to find these cumulative probabilities, I can use that norm.dist function, right? I've got these two cutoff values. I'll know the mean. I'll know the standard deviation. There we go. So what I can do, let's say I wanted to find the probability that I'm between 70 and 72. And I could take a little bit more time and make sure I put the equalities on there. But we said it doesn't really matter since the probably of any one specific value is 0. So I'm just think about I'm in between this range. I could do norm.dist, use that value of 72, comma, here's the mean June temperature, comma, here's the standard deviation, comma, make it cumulative. So that gives me the area to the left of 72, right, this kind of blue circle. I'll then subtract from that norm.dist, the lower value 70, comma, select the mean, comma, select the standard deviation, comma 1. Oh. That second part would give me the area to the left. So when I subtract that kind of little area, that red area there from the entire blue area, I'm left with just what's in between those two. And I can do this all in one cell. I don't have to like do it in parts. I can use the norm.dist function multiple times in the same cell. Any questions on that? Okay, so if I hit enter here, oops, I can find that probably. If I had done this a little bit more appropriately and I used cell references here, then I could have like changed those and now I have to go into the function and like I would have actually put these numbers like, I don't know, somewhere over here so I could reference them. Yeah, yep. So, but that works as well. Okay. Questions on that? Okay. The next thing we'll talk about is, so what we were doing before was I was starting out with some value for x. I was turning it into a z-score and then finding the area to the left. Okay. What I now am going to think about is, well, what if I knew the area I wanted to the left? I could figure out what z-score gives that to me, and then using the inverse transformation formula, you can plug in that z-score, the mean and standard deviation, and figure out what x value that is, right? So we're kind of working in reverse or working like the inverse. Oh, sorry, I didn't mean to have this up here. Here's my inverse transformation formula. So I'm working kind of in reverse or inverse, right? So if this is what I want to do, well, let's have this leave this open down here. I'm going to get rid of this real quick and just leave the information. that looks similar to an example we did last Friday. So we had this test score, the average was a 72, and the variance was a 64. And we said, okay, what's the cutoff for the 90th kind of percentile, or to be in the top 10%? So right, 90% of the test scores would be below you. So there we knew the area that we wanted in this left tail was 0.9. We then want to find the z-score that gives us 0.9 in the tail, use the inverse transformation formula to figure out what x value that corresponds to. So, I'll show you a slightly different way of doing this. So we'll do the alternative way first. So if we use the norm.s.inv, what this will do, instead of you telling it a z value and it returning to you the probability of seeing that z value or anything below it, you'll tell Excel the area that you want in that lower left tail, or the probability of seeing that z-score or less. So you know you want it to be 0.9. So it will give you the z value that gives you 0.9 in that lower left tail, and it does it out to more than just the second decimal. So when we did this by hand on Friday, you're limited to the second decimal point, right? Here, I could tell it any probability. Now I could tell it, 0.904513, whatever. And it could be very exact. So I'm gonna undo that though and just do 0.9 here. Okay. So now that I have that z-score, I just plug everything into my inverse transformation formula. So it's equals the mean plus that z-score times, now here's where I have to be careful. It's multiplied by my standard deviation. All I have is the variance here. So I could just do the square root of the variance, and that calculates my standard deviation here. Or I could do it like in a separate cell and then just reference that. That might be a little bit easier, honestly. But I want to make sure you know that you can do this as well, right? If I have the variance, the standard deviation is just a square root of the variance. And sure enough, I get about an 82.25, which is exactly the same thing that we found on Friday when we worked through this example by hand. Might have been off a little bit at the third decimal point because we had to round things in order to use that table. And Excel doesn't have to round things, right? Any questions on that? Okay, so I can sidestep calculating the z-score. Like I don't really need to see this. The only reason I find it is so that I can plug it into this inverse transformation formula. Excel will do all the work behind the scenes for me. So instead of using equals norm.s.inv, if I just use norm.inv, once again, there's no s. That .s tells it it's a standard normal distribution. I'm using z-scores. This tells it I haven't converted it into a z-score yet. So the area I want is 0.9, comma, here's the mean of the original variable, comma, here's the standard deviation. Well, once again, I'm going to have to take the square root of that variance. That would give me the standard deviation here. Now what Excel will do is it'll look up that z-score that gives you 0.9 in the lower left tail. It'll use the mean and the standard deviation you told it and then plug those things in and then return to you the x value that would give you that 0.9 in the lower left tail, which should have been the value that we came up with down here as well. Right? So kind of two different ways of doing the same thing. The second way just cuts out a lot of the in-between work, right? It kind of trimmed up and cut out a lot of, just a little bit of extra work and did a lot more of it behind the scenes, or what I would call black boxing it. Now, we also did in class, like what's the cutoff for the bottom 40%? So instead of like putting the number in here, if I just click on the cell reference where I have the probability of the area that I want in the lower left tail, notice I can come up with all kinds of cutoff scores for whatever, whoops, if I put it in the right cell, for whatever area in the left tail I'm interested in, right? So one thing that, what if I put 0.5 in here? What test score should give me an area of 0.5 to the left? We know that the area to the left and the right of the mean is always 0.5, right? So if I put 0.5 in there, what test score should give me 0.5 in that lower left tail? Well, it should just be the mean, right? Because remember, this norm.inv function I'm telling it the area I want in the tail, and it's going to tell me the test score or the original value for the variable x that would give me that. Now, if I'm thinking about what z value would give me 0.5 in the lower left tail, the z-score that should give me 0.5 in the lower left tail would be 0. And notice my inverse transformation formula, if the z-score, like if I wanted, the area of 0.5 to the left tail, that z-score should always be 0. 0 times anything is 0, so the cutoff value I'm always going to get is that mean. Sure enough, that's what happens. Now, that's not the most interesting example. It's probably more likely we want to do things like find the 90% cutoff or things like that. Any questions on that before we keep moving? All right, I think we have a little bit more time than the other class, so I think I'll go through this just to kind of show you the power of Excel, and it's kind of interesting. But I don't want you to get too far ahead of the other section because I know we worked through a little bit quicker here. So I have this whole thing that I built. I was thinking of maybe making you guys do something like this, but I decided it's too difficult or outside the scope of this class. But I do want to show kind of what we can do in Excel and the power that it has. So notice I have the thing set up here like it's one of those Z tables, right? So I have the first decimals here, second decimals here. Right? So what I did was basically, if I wanted to say, so let's just say, for instance, I have this Z value of negative 4.0, right? Well, if I use the norm.s.inv, if I tell it negative 4, not inv, sorry, .dist, if I tell it that z value of negative 4 and make it cumulative, it'll always give me the area to the left. So that's essentially what I did here. It's the same value. But the value I wanted to do is I need to take kind of that 0.4, right, and then add to that, right, the second kind of decimal. Okay? So it's a little bit more difficult than what I originally thought to kind of do that. But basically, each one of these cells is taking this, and here it's going to negative 4.01, negative 4.02, and 3, right? And that's the value that it's using to put into that norm.s.dist function. Okay? So like I said, it's a little bit complicated. I needed an if statement because when it's negative, then I actually needed to subtract this, right? Because it needs to be negative 4.01. So if I added it, it get closer. It was, thought it would be easier than it was. But anyways, so I got this kind of where we're putting each one of those in. And notice, like, I use this thing that we're not going to have to use in this class, but I just want to show you the power of Excel. When I only put $signs on, like, the column reference, it freezes the column. But then when I copy it over, sorry, it's only on the row here. It freezes the row, but then it allows the column to update from B to C. All right, it keeps it at 1. So I use some, kind of tricks of Excel, but basically you can build your own contingency table, right? This is just like the table that I posted up as a PDF. And, just to kind of verify, once I get to 0, hopefully I'm at 0.5, right? And sure enough, I am. And then I can kind of check out these other kind of common values like 1.29, 1.28. Those are the ones that are really close to 0.9. So, this is kind of, showing you the power of Excel, and you can do this pretty quickly. As opposed to like actually sitting down and doing all this integration by hand to build this table like they would have used to have to do. So kind of interesting to just see the power of Excel here. I wanted to make sure I brought that up. So if there's no more questions about the Excel, I think we'll kind of jump into the next topic here. So check the chat before we move. All right. So, that's not what I wanted to do. There we go. So now I got everything. Okay, perfect. So, here's some of the functions that we use today. I showed you the norm.s.dist and the norm.s.inv as well. But just kind of a reminder, this is kind of the format in which we would use them. So the next thing we're going to talk about is all of this discussion about normally distributed variables has actually been I haven't explicitly defined it, but that we're thinking about population data. Now the problem is, we usually have these populations, so infinite or finite, and most are finite, right? Like even if I think about the U.S. population, there's a finite number of people in the U.S. or a finite number of people in the world. So often we're dealing with finite populations. Infinite populations are like usually from some data generated process. But the problem is we can't get population data. We can't get the entire population. I mean, sometimes we can use a census, but even then we're not usually capturing everyone. We're getting a vast majority. So we're stuck using a sample to make inferences about the population. Okay? Now, one thing we want to be concerned about is if I'm trying to take a sample, our ultimate goal is to have the sample be just as representative of the population as it can be, right? If we end up with a random sample of 100 people and every person in the sample is over the age of 70, that doesn't help me make a lot of statements about the US population as a whole, right? I know my sample looks nothing like my general population if everybody in my sample is over 70. So what I can do is I try to sample randomly. And when I sample randomly, I'll end up with a sample of size lowercase n out of the entire population, which is capital N, right? So capital N would be like, the US population of 300, whatever it's at now, 20, 30 million, something like that, 320, 330 million. And then our sample size would be, maybe I take a sample of 1,000 people. There my lowercase n would be 1,000. So I can do this with and without replacement, and both ways are fine. But if you think about, let's say I had everybody in this class and I put all your names in a hat and I start drawing your name out, and maybe I'm interested in like the average height of a Ball State student or something. So I pull out the first person's name, I write down their recorded height and their name. If I'm doing this with replacement, I would put their name back in the hat, then draw a name again. So if I do this with replacement, what's one of the possible things that could happen? Well, if I only had a smaller group of people, like this class isn't that large, eventually as I'm drawing names, if I keep putting the names back in the hat, at some point I'm going to draw someone's name twice. And in my sample, I don't, if I have the same observation twice, it's essentially going to carry more weight than the rest of the other observations. I usually don't want this. If I am able to, I don't want to have more than one person be any more than one observation in my data set. But if I do it with replacement, that can happen. So generally, 99% of the time, it's better to do sampling without replacement, right? Once I draw someone's name out of the hat, their name doesn't go back in. It's a way to think about it. Now, we're not going to be actually conducting or running any surveys or samples, but to understand the biases that could exist are important, so I want to make sure we kind of start out with this, right? We'd like to do it without replacement. So once I get this sample, it's fine, but I need to make sure a couple things are true. One, I need to make sure that every element comes from the population, or every observation comes from the population. If I'm interested in US income, and I randomly sample people, and I don't know what method I used, but somehow somebody ended up on my list of people I contacted with, and they're actually a Canadian citizen. Well, I don't want them in my sample because they're not part of my population, right? So that generally isn't something we have to be too concerned about. I do want to make sure that my observations or my elements are selected independently, right? I use this word element. This is kind of the technical. I'll typically just call these observations. The fact that them being taken independently really only gets broken usually if we're being lazy, like something like I'm doing phone surveys and someone finally answers and talks to me. So I ask if somebody else in the household would also want to take the survey. Well, now those two observations are independent, right? They're from the same household. They likely have same underlying characteristics. So it's not difficult not to break this rule of them being independent, other than if we're being a little bit lazy and just trying to get something because it's easy. So even with this in mind, we have kind of an additional issue. So I'll use gender because it's easy to think about here, and then I'm sure there's a longer discussion about this. We're talking in generalities here, but imagine like we look at the U.S. population as a whole, it's on average about 50% men, 50% women, right? A little bit off one way or the other. Maybe it's like, I don't know, 48, 48 or something, it's not that big a deal. It's about 50-50. We know then if we have a sample, let's say I'm interested in like calculating the average height in the US or different countries. Well, I know it's going to be about a 50-50 male to female ratio. If I end up with a sample that has 80 men and 20 women, well, now any statistic I calculate about height from my sample is going to be biased, right? It's not going to match up with the population because I know that my gender composition of my sample doesn't look like the gender composition of my population. Gender is one of the things we could think about. There's going to be a lot of these characteristics. Maybe I want to do this by income, right? I want to make sure my sample has an income distribution that looks similar to the population, okay? So what I'll do is I'll divide my population into these little subgroups, or we call them these strata, so they don't overlap. So this would be like, we'll do an age one. So let's say I want to make sure that I have an age distribution that looks similar to the US population as a whole, right? So what I might do is say randomly sample 10 people from the age of 0 to 10, randomly sample 10 people from the age of 11 to 20, randomly sample 10 people from the age of 21 to 30, kind of so on and so forth till I get to the, the very highest age. Now from each one of these age categories, I'll have a random sample of 10 and then put them all together to get a much larger sample. Or, so we're thinking about we divide them into these stratum or these non-overlapping groups, these different age categories. Then once I randomly sample from each one of those age categories, throw them all together to get my full sample. The other maybe easier way to think about this, if we go back to the gender example, maybe I randomly sample 50 men, randomly sample 50 women, throw them all into the same kind of full sample, right? That way now I know my full sample has a gender kind of distribution, I guess, that looks similar to the population, or a gender composition that looks similar to the population. And usually, you usually want to do this when you know that there's groups within your population that will impact the variable you're looking at. So, if I'm looking at height, I know that gender composition would really matter in my sample, that it looks similar to the population. Or if I'm thinking about maybe something like, I think I did this one in a second, but if I know that different income categories tend to vote more one way or the other, more Republican or Democrat, well, then I want to make sure if I'm looking at a sample to try to predict the outcome of an election, that the income of my sample looks similar to the distribution of income in the US. So the other one that is a very similar idea, but just a little bit different, is cluster random sampling. So with the stratified random sampling, we would think about, we're separating into these groups where there's no overlap, right? You can't be, we do it by age, you can't be 11 and 25, right? Like you're only one of those ages. So the problem is, what if we did something a little bit different, which is, I want to make sure that the entire country is represented in my sample. So maybe I randomly sample, say, 10 people from every state, right? Now, I know that probably doesn't make a lot of sense in that there's a higher population in California versus Rhode Island, but maybe I want, maybe it's like the Senate. I want to make sure every state is represented, right, equally in my sample for whatever reason. Well, if that's my goal, I could randomly sample from my subpopulations, right? States are subpopulations of the entire US's population. So I could randomly sample 10 people from every state and then throw them all together, all right? So randomly sample 10 people from every state, throw them all together to get kind of my full sample, right? So divide it up into these subpopulations or into these 50 states, randomly sample 10 people from every state, throw them all together, 10 people from 50 states would be a full sample of 500, right? So it's a very similar idea to stratified random sampling, other than it's usually used for like geography, right? Where I'm trying to get every region represented. And it's not really like, I guess it's kind of the same as stratified random sampling in the sense that I can only be from one of these cities, but it's not stratified in the sense that each one of these cities could have, each one of these states could have actually similar characteristics. They're just a smaller scaled version of the entire population. So, we could use a combination of cluster and stratified random sampling if we wanted to. We're not going to do this in practice. I just want to bring this idea up so we can start to think about our main goal is to get a sample that is as similar to the population on every one of these kind of metrics as possible, right? You know, so political polls do this a lot in terms of using this cluster sampling, where they'll break the country up into regions to make sure that every region is kind of well, not, I shouldn't say equally represented by this as the same percent as they are of the entire population, but still making sure the West, the Northeast, the Midwest, the Southeast are all kind of we end up with a number of people from each one of those regions that matches what the country's kind of population breakdown looks like. So we see this used a lot in political polls, and we'll think a little bit about this in our next example, except for I think I had this slide that, I don't know why I put in there. This is basically the whole discussion is, we can't get a sense, it's not often we can take a census, so we're stuck with using this sample data. So how can we better use this sample data? We know that there might be biases that exist. We know that it might not be a perfect representation of our population. So where do we go from here? All right, so we'll start setting this up, thinking a little bit more about biases, okay? So the example I'll use, and we'll start it today. I don't think we'll get through it all. I'll probably end class a little bit early, so we're sticking with the other section. But if we go back to the 1936 presidential election, Alf Landon was the Republican candidate at the time who lost to Roosevelt, right? Lost to FDR. So in 1936, prior to the election, my grandma used to get this little book. It's like kind of like a magazine, but the Literary Digest poll sent out 10 million survey cards, right? So sent these surveys out to 10 million people, and they got 2.5 million people to respond. So they've got a sample of size 2.5 million. Which that's pretty good, right? Especially in 1936, that was an even larger, proportion of the population, and it's also just a large sample, 2.5 million people. And they asked these people who they plan to vote for in the upcoming election. Right? Now, I don't know if you've talked about this in other courses. I'm sure marketing does a little bit more of this, but even the response rate here, 25% is an insane rate. Like they were probably very happy with this, right? They're like, holy cow, we're going to be able to easily predict this election. No, I mean, I don't know if you get 2.5 million people to respond to an email, let alone out of the 10 million. So, this was good. And when they looked at these 2.5 million surveys, they predicted that there was going to be a landslide win by Landon, that he'd win 57% of the popular vote and kind of a pretty sizable victory in the electoral votes. Now, we obviously know that didn't happen. But not only were they wrong, it wasn't even a close election, right? Roosevelt won in a definite landslide, right? 523 of the electoral votes. I mean, they were predicting 370 to go to Landon. They were way off, right? So how did they get this so wrong, right? Did they make mathematical errors? Was, there's some kind of formula they were using that was incorrect? Well, those aren't very likely, right? They had good people working for them. But what if those 10 million cards were sent only to Republican voters? Well, then I'm going to have a skewed sample from the population, because I know that at any one point in time, not just thinking about the people who vote. I mean, if we look at kind of voting outcomes, like it's maybe a little bit higher than 50-50. But if we look at like registered Democrats or registered Republicans that vote, it's pretty close to a 50-50 breakup, right? It swings a little bit every 4 years, one way or the other. But if we mailed only to Republicans, well, we definitely now have a sample that doesn't match the population, right? What if they sent 5 million to Republicans, 5 million surveys to Democrats, but not a single Democrat responded, but 2.5 million of the 5 million Republicans responded? Well, it's a different kind of bias, but we end up with the same problem, right? I have a sample that would be overrepresented by Republicans relative to the population as a whole. So let's think about kind of how we can maybe talk about these two biases a little bit more generally. So we would usually call this the selection and the non-response bias. So the selection bias is if I systematically select or send a survey out to a certain group, right? So if I systematically were sending more postcards to Republicans, that's a selection bias. It's often easy to kind of deal with these, right? If I want to eliminate the selection bias, well, I just sent 5 million to Republican, 5 million cards to Democrats, right? And now I'm good. But the non-response bias is a little bit more difficult. So the non-response bias was the idea that, well, even if I sent an equal number of survey cards to Republicans and Democrats, if only Republicans respond, that was my non-response bias. One group was not responding, right, to my survey or to the question I'm asking. So we probably had both of these maybe going on, but it seems like we could definitely deal with a selection bias. So we'll first think about that selection bias in that Alpha Landon example, right? So how were they selecting the people to send these survey cards to? So what they did was they were getting names from a cross-listed database, and the cross-list was telephone books and car registration. So the only people in this database were people who had a car registered to them in their name and had their name in the telephone book. In 1936, who owned both a telephone and a car? The Uber, the very wealthy, right? 1936 to have a car was pretty wild. I mean, to have your own telephone line, there were still people where, you know, you'd have these country blocks where people were like, the whole block was on the same phone line, right? So to have your own kind of number, it's a little bit, you know, we were looking at a different type of people in 1936. And if they tend to be wealthier from this group, we look at kind of voting habits. Wealthier individuals tend to lean a little more right? So we're tending to get more Republicans from a selection bias here that exists, right? So there was these researchers, and they went back, I forget what year it was, not too far, like 20 years ago maybe, and they were able to interview people who voted in the 1936 election and figure out and ask them at the time, did you have a car and a telephone? Did you have a car only, or did you have a telephone only, or neither? And then who did you vote for? And what they found was, you know, like I said, whatever year they did this survey after the fact, people who had a car and telephone, 53% actually did end up voting for Landon. So the 57% prediction wasn't that far off. The problem is when they found people that only had a car or only had a telephone, they voted for Landon much lower percent, right? And 60% of them approximately voted for Roosevelt. But these people weren't showing up in our database. So if the digest had simply used like the combination of do you have a car or a telephone, they probably would have made the right prediction. But this database they had came from just this cross-listing. Now, what's even crazier is if people who had neither, right? This is probably going to be people who, not a lot of money in 1936, you don't have a car or a telephone, you're kind of lower half of the income distribution. 73% of them ended up voting for Roosevelt. So this is why, you know, the total election ended up being such a landslide. And you can kind of see what's interesting here, like the total breakdown. So it's like about 27% of people owned a car and a telephone at the time. 37% owned neither. 30% had a car only, and about only 6% had only a telephone. So like it's more likely if you get a car and then you get kind of a telephone next. Right? So kind of interesting results there that really kind of highlight the selection bias. If we're using a process where we're over-selecting from this group, we end up getting skewed results relative to what the total kind of population voted as. Okay? I think like I said, I want to start the sections off at the same place, and we kind of got only this far with the last section. So we'll pick up on this example on Wednesday. We'll talk through, we already went through the selection bias. We'll talk through the non-response bias in this example. And then we'll talk about a few more biases we can see, think about a few more situations, and then we'll eventually get to where we're looking at the distribution of sample means, okay? So we will do that on Wednesday. I'll put an online quiz up when I get back to my office. That'll be due before class on Wednesday. Also, that next Connect assignment is up there on Canvas. We can probably work through at least the first half of it at this point. By the end of the week, we'll have covered all the material where you can get through the entire thing, okay? All right, enjoy the beautiful weather today, and I'll see you guys on Wednesday.